Thank you very much, and good afternoon, everybody. It is a real pleasure to be here at the Royal Society today for the Summer Science Exhibition and give you this talk, which is Under the Lens, the Edible Chemistry of Baking. So hopefully, during this talk, what we're going to do is we're going to showcase to you some of the hidden science behind the foods that we eat, and we can progress through from what we see by our eyes through to using microscopes, so we can see things on a micro scale, and then talk about on a molecular level as well what is going on. I am Josh. I'm a researcher in chemistry at the University of Leicester. I'm a science communicator there, and as introduced, I was also on the Great British Bake Off, but we'll get onto that in a slide's time. So, without further ado, let's begin. So I'd like to start off, just as we've done the introductions, on from the lab to the tent. So I'll ask first, how many of you have either watched or heard of the Great British Bake Off? Phew, that's all right then. So you should be familiar with the format. So if you watched it 3 years ago, you'll have seen me on your screens, and I got through all the way to the final. So if you haven't watched it, go and watch it, and I'm on all 10 weeks. So it's there for you to have a little look at. So here's me on finals day with my fellow finalists and the presenters and the judges. So it was the most amazing experience. I've watched it since its first series. Never for one moment did I imagine that I would actually be in the famous white tent. So that's me on the right in the tent. On the left there is in the chemical biology lab at the University of Leicester. And as you can tell, I love my experimenting. So whether it is in the lab with my lab coat on, experimenting, doing my chemical reactions, or whether it is in my home environment in the kitchen and experimenting now with my apron on. So I love both of them, and there is an incredible amount of parallels between chemistry, science, and food. It's in particularly baking more so than cooking. I know a lot of people will say with cooking you can sort of like recover a bit and you can be a little bit sort of heavy-handed with adding bits in. With baking, it really is an art, and it really is. I think baking and chemistry really do mix together very well. So I say baking is a science. I like to start off with showing you a reaction scheme. Now this is the reaction scheme for making aspirin, and I put this up because I vividly remember this being one of the first practical experiments that I did at GCSE A-level, so some of you may be doing it, or you may be doing it very soon at school. Classically one of the assessed practicals that you do to make aspirin anti-inflammatory. It's a painkiller for mild pain relief like headaches and fevers. But I vividly remember doing that in the lab with my chemistry A-level teacher, which is Mr. Reed. And we take our salicylic acid, we've got our acetic anhydride, I mix them in a flask above a Bunsen burner. I say Bunsen burners, but in the labs we never use Bunsen burners now, but I know at school we still do. And we make aspirin. But for me, it was one of the first times where I really saw, but doing this practical chemistry, how much it just mirrors exactly what I love to do, which is baking at home in my kitchen. I bake for my entire life, and then when I start to meet doing lots of these practical experiments in school, I know this is what I love to do. I love chemistry. It's just like being in my kitchen, getting to experiment and make something new at the end. So exactly the same way that you can make aspirin, whether we're making our bread, so this is one of my sourdoughs, or making a nice strawberry and cream cake there, it mirrors very much the same. You've got your ingredients or your reagents, we're mixing them together, we're heating them up, and we're getting a new product at the end. Also things like for making the aspirin, you'll see at the top we have got our this is sulfuric acid as a catalyst, so that's a catalyst. What it does is it protonates our acetic acid there, and what it'll do, it just helps to speed up that rate of reaction. But in the same way that we've got catalysts to help speed up that reaction, we have things like yeast for making our bread. Yeast also has got enzymes there to help break down our starches, and then we're going to then ferment the glucose formed to help get our lovely risen bread. And in the same way, we've got baking powder when we're making a cake, which although not acting as a catalyst, in a similar sort of way, we're adding a very, very tiny amount, and it makes a massive difference to our end product. So there is a lot of parallels between those two. So what we're going to do is we're going to journey you through a couple of little bakes along the way, and we're going to showcase some of the science behind it and show you some wonderful microscope images. So we're going to begin with the bread. So we're going to start with my sourdough. And what do we need to make bread? So we need our flour, and we make our flour from wheat grains. So here is a grain. So I went and grabbed a grain, and I've imaged it under a little microscope, a little optical light microscope. And then here's the grain. I've cut it in half, so we can see the contents. And what we've got there, we've got our bran, endosperm, and our germ, and these are the three main components that we've got. we have got the bran is containing a lot of the fibre that we have. So if you have whole grain flour, you're going to have the bran in there as well. So it's got lots of fibre in. The germ's got lots of the nutrients. We've got vitamins, minerals, and fats. But it's the starchy and protein-rich endosperm that we have to make the classic white bread flour that we have got to make our bread. So I've said starches and I've mentioned proteins. And now we'll have a little talk about what are they doing, and how are they helping us to make a wonderful bread. So here we go. We're going to go through gluten proteins first. We're going to go through starches second, and showcase to you how just by mixing some flour, bit of salt, bit of water, and some yeast together to make a dough, there is an incredible amount of science and chemistry that's going on in that bowl. So anybody at home that does any bit of baking, you're all scientists already doing it. So we're starting off with our proteins, so gluten proteins. These are the two main families of proteins that we have in our flour. For our gluten proteins called glutenin and gliadin. So glutenin, these long chain-like proteins, and they're helping to provide the stretch that we've got in our dough, so it's the strength of that dough and the elasticity so that it holds its shape. And then we've also got these gliadins. These are more globular, more compact, and they're helping to provide the extensibility so that you can stretch that bread dough once you've built up the gluten without it tearing and get your lovely window pane test. And how I like to describe them is think a little bit like spaghetti and meatballs. We've got the long strands, we've got the globular bits. And what we do is once we are making our bread, the first thing we do is add a little bit of water, and then we're going to make our dough, and we're going to knead them together, and those combined create our spaghetti and meatball mixture, which is our gluten, which is helping to provide that wonderful texture, structure that we've got into our dough. There's lots of, in their natural state, these proteins got lots of interactions in between them, between the amino acids and the side chains that they've got. But when we're kneading our bread, what we're doing is we're repeatedly breaking and reforming some more interactions. A lot of these are cysteine covalent bonds, disulfide bridges that we've got between those proteins, and we're repeatedly breaking and forming new ones as we're kneading that dough to help build up this wonderful matrix, which is then going to capture our bubbles of gas, our carbon dioxide, to help us get a lovely risen bake at the end. So that's our gluten. Then on the right-hand side, we have got our starches. So we've got amylose and amylopectin, our two starches that we've got there. These are these complex carbohydrates. And these are energy storage. So you'll see that they're all linked together. That we've got, they're made up of purple hexagons. Each one of those purple hexagons is to represent a molecule of glucose, which is a six-membered ring sugar. And they are all joined together. So glucose is what we get as our source of energy. When we access glucose, when it's either broken down to glucose or when we have glucose absorbed into the bloodstream, help provide and fuel our cells. So we want to get access to that. And we've got our starches to access the glucose that we then also need to help for the fermentation process to help leaven our bread. Those starches get broken down. This is where we can bring in enzymes now. So these are the catalysts, like we mentioned for the catalysts for the aspirin at the start. We've got enzymes coming in. They're going to act very, very specifically. They can cut these starches now at very, very specific points along those chains, and we can break those down now into the glucose that we need. So we have glucose to help provide us energy, but also glucose as a reducible, fermentable sugar we need when we have the yeast coming in, and that will convert the glucose into carbon dioxide and ethanol. So one molecule of glucose will create two molecules of carbon dioxide and two of ethanol. So you can see there the amount of science and chemistry that we can access just by making a very simple bread dough, making a sourdough at home. So I mentioned I wanted to showcase microscope images as well, and sort of like show you up close what's really happening, and we're going to focus on the yeast. So what I've done is I've been and grabbed some of our yeast, and we've gone and imaged it under an electron microscope. So here is the image. So this is some fresh yeast that we've looked under a microscope. This is to showcase to you how we know yeasts they're living, single-celled organisms, and we know they're multiplying, dividing. Anybody that has a sourdough starter at home, we know that we're continuously feeding that starter because those yeasts are growing and they're feasting on the nutrients that we're giving them, and they're continuously multiplying. Here are the yeasts. So what we've got here, this is a 500 times magnification, and you can see the scale there. So that bar is showing 20 micrometers, just that bar. So I would say probably across there, let's say we've got, I don't know, 150 micrometers maybe. The width of a hair on your head is around about 80 to 90 micrometers. So I would say you've probably got 2 hairs' widths across the entire page there, or the entire slide. That's how small we're looking. And we can go a bit closer now, we can zoom in a bit closer, and you can see now we're down to 3,000 times magnification, 3 micrometers. I'd say we're at 20 micrometers across that slide. 4 widths of that slide is the width of 1 hair on your head. So that's how small we're talking about here. And we've got millions and billions of these yeast cells in our yeast. So if you've got 1 gram, about 1 gram of yeast, it's going to have about 20 billion yeast cells in there. And you notice here that you can see these little lumps forming on the yeast. So this is the process by which these yeasts are dividing. So they divide by an asymmetric division budding process. So they form these little buds on there, and then they grow off the mother yeast cell. They're growing a new daughter yeast cell now. And that's that budding process by which they multiply. And I'd like to showcase and talk about that because it mirrors very much how my research when I did my PhD at the University of Leicester. I was chemical biology, so I used to synthesize my molecules in a chemistry lab, and I was not looking after yeast, but I had some colon cancer cells over in the biology lab, which I had to continuously look after and culture. So I was repeatedly going there and having to look after these cells and keep splitting them because they were always growing. So I'd have to every day, every 2 days, I have to go there, I have to take a little bit out, put onto a new plate so they can continuously grow because they're always feeding off the media, and I have to look after them. So it's in a very similar way. It's a nice way to link up, actually, what we've got in a baking context to what we're doing in research as well. So that's the yeast. We can then go even closer now. So now we're down to a single 1 micrometer. So again, let's say we've got 10 micrometers across the width of the slide, 10 of those for one width, for the width of 1 hair on your head. So that's how small we're looking. Now this is fresh yeast. You'll see at the bottom it says fresh. But what we typically use in our breads, we've probably all got a pot of dried yeast at home. So let's have a look at one of those. So here we are, here's our dried yeast now. So you can see that's a single little pellet, the tiny little pellets that you get when you've got your dried yeast. And you can see that's one of them. If we zoom in on the surface, you can see these millions of yeast cells there. And we can zoom in again, and you can see that they're exactly the same. They're in their dormant state. All the moisture's been removed. They've slowed down their metabolic activity now. But then once we add them into our dough, and we add a bit of water in there, bring them back to life, and they get going again. So we've done fresh, we've done dried yeast, but I showed you a sourdough. So I now want to bring in a sourdough starter. So here we go. Here's a little vial with my sourdough starter in, and I'm going to showcase to you what instruments we've been using to actually create these wonderful images for you. So what we've done is for all of these, we've put them under an electron microscope. This is our Gemini electron microscope. We've prepared the sample, and we've imaged them under here. To prepare these ones like you would do preparing any biological sample. So these sourdough starter, we know have got a lot of moisture in there, and that's not going to be very good for creating an image under vacuum for the electron microscope. So what we have to do, we have to prepare that sample. And we prepare that via a process called critical point drying. And that is now what we first of all do. We're going to replace the water in there with a solvent, so either ethanol or acetone, and then we mix into there some supercritical CO2. And then we get rid of that by playing around with the heat and the pressure. So we can then, the liquid supercritical CO2 goes from supercritical through to back into a gas phase. We've now got no moisture in there at all, and we're left with a beautifully preserved sample that has got no collapse. So if you were to just take a sample and let it dry out, just leave it out to dry, you would lose some of that beautiful detail. So we prepare this exactly the same way we would do any of our biological samples. It's also then coated in a thin layer of gold. So we want to do that because for this, we're firing a high energy beam of electrons. And we've got a non-conductive surface at the moment, so what we'd end up with is a lot of charge build-up. We'd lose the resolution of that image. So we have a thin coating of metal, so we've got gold on there to help to reduce that and give us a wonderful image. So I've built it up now we're going to show an image. So hopefully what we've got here is an image of our sourdough starter. So here we go. And this is going to now begin to piece together all the bits that we've talked about already in the talk. So I mentioned at the start, I mentioned starches. Well, the starches are stored in these starch granules. So when we're mixing and then we're baking our mixture, these are going to then begin to gelatinize. They're going to release all those starches into the mixture. Here is one of our yeast cells. We've already met those earlier. But then the other thing that we have with sourdough is that we know we have that sour tang to it. And that's because as well as having the wild yeasts in there, we also have lactic acid bacteria and acetic acid bacteria, which are producing organic acids like lactic acid, and that is going to produce that sour tang that we get into our sourdough starter. So we have got all of these in our sourdough starter at home. So who's got a sourdough starter on their shelf at home? A few hands, that's great. So this is what's going in there if you looked at it up close. I usually, if I do a tasting demo, I usually let people taste my sourdough first before showing them the image, because it looks a little bit gruesome. That's what we've got. But they are helping to provide that they're acidic, they're going to lower the pH, and they're creating an environment which is going to promote. These are all really healthy bacteria and yeast. They're really good for you. Having that acidic environment is helping for these to thrive and preventing any bad bacteria from being able to emerge. So that's our sourdough starter. I've done bread now, and now we're going to go on to a different bake. And I thought, given that we're at Wimbledon at the moment, I thought we'd do something connected with strawberries and cream and meringue. So here is Science of Meringue. So it also works really nicely because on the Great British Bake Off, I did a Wimbledon-themed meringue showstopper. And it still stresses me to this day, the week leading up to this, we had to make these meringue bombs. Now, anybody that's made meringue at home, you'll know that you bake it on a very low temperature for a very long time. But in the Bake Off, we haven't got time because they only give you a set period. So we had to try to bake this meringue so it was like concrete and have the whole thing decorated inside about 3 hours. And it had to have a reveal dessert on the inside as well. But it all worked. So that's that one, and that's one of the meringues that I've made. And although I haven't brought any tastings along, typical whenever I do my talks, I usually give a recipe or an ingredients so that people can, after you've listened to the talk, you can go away and you can have a go at making this yourself at home, and hopefully you've remembered all the science along the way as well. So you can all get a copy of this. I'll make sure it's available if anybody wants to have a go at making their own meringue at home. But now let's talk about some of the science we've got going on. So we're going to first of all return to sugar again, because we've mentioned it a little bit earlier on. And we're going to look at, here is sucrose. So sucrose, or table sugar, is the sugar that we're typically using in our cakes, putting a spoonful into our coffee. Here is sucrose. And this is a disaccharide. So di meaning two, so it's got two sugar units bolted together. So you can see those just there. If you were to split those in half now, and you can do that enzymatically using invertase, you would invert that and you would now make two monosaccharides. And these two monosaccharides are glucose and fructose. So we're meeting glucose yet again here. So glucose we've already covered. Fructose, also known as fruit sugar. So it's high levels in lots of fruits. You'll get it in things like honey as well. And these ones, as opposed to sucrose being very crystalline, those ones are more syrupy. And you're familiar with that because I'll use glucose syrup in things like making caramel so it doesn't crystallize at all. And also glucose there is an instant source of energy. I play rugby during the winter months, and I will have a glucose sachet. If it's a hot day like today, I've got rugby training tomorrow night, I might have a glucose sachet with me so I get that instant energy when I need it. And then just for completion, because we've already covered it earlier on, that's the monosaccharides, but then if we had loads of those glucose all bolted together, we go back to our starches and our complex carbohydrates that we covered at the beginning. But what I want to focus on, what we're using for meringue, we're using normal sugar, table sugar, so we're going to look at sucrose. So, different forms of sucrose that we can get in the shops. Granulated, castor, icing, they're all sucrose, just to a different level of refinement. Now we'll add on the microscope images of each one, so hopefully they can all now emerge. So here we go, we've looked at them all. So you'll see that the scale, 100 micrometers, is the same on each of those ones, so you can see so that you can compare those relative. And that's what we expect. We know that the largest crystals we get with the granulated, and we go finer down to icing sugar. But which ones do we use for different uses? Well, for meringue, the best one to use would be your castor sugar. They're nice, sharp, small crystals. They dissolve well into the egg white, so that you don't end up with any gritty bits in your meringue, but they're also nice and sharp, and they help to build up a nice, fluffy meringue. The granulated ones, they're much bigger, so you can see they're around about 5-6 times bigger. So we've got a scale of 100 micrometers there. So let's say that's about 600 or 700 micrometers across. That's about 0.7 of a millimeter, so less than the smallest increment on a ruler. That's what we've got on the left, which is typical. Well, we know what size granulated sugar is. But those ones, they don't dissolve quite as well. So if you're making meringue with granulated sugar, it doesn't dissolve quite as well, and you can be prone then to your baked meringue being a bit gritty, or that sugar then dissolving during the bake, and you end up with a meringue that might weep around the edges a little bit. So castor sugar is the best. And you may say, well, Josh, why don't we use icing sugar then, because that's the smallest? Well, icing sugar, that is the greatest level of refinement, so they are the smallest, but it's not actually just pure sucrose for icing sugar. So you'll see on the back it might have an anti-caking agent in, so something like corn flour, rice flour, and that's because sugar is very, very hygroscopic. So it loves to grab onto water and moisture. So if you don't have the anti-caking agent in, then it can be prone to your icing sugar clumping up quite a bit. So if you just use icing sugar, you can get maybe a slightly floury taste in your meringue. So castor is the best. So we've done bit of proteins at the start. We've done sugar, biochemistry, enzymes, yeast. We're now going to go back into proteins again. But for the proteins now, we're going to now go one step further now and actually see what the protein's made of. So here is a protein, because we're going to build into now talking about our egg whites and the proteins that they contain. So here is a protein. Proteins are, well, made of proteins. Proteins comprise of building blocks, amino acids. We have 20 that comprise the proteins that we have in our body. And these are all identified by this 3-letter code for each one. And you can see I've slightly separated those out. I've slightly separated those out because we have essential and we have non-essential amino acids. And each of these ones are different because they have a side chain on them as part of them, and that side chain invokes different properties and makes each one of those amino acids unique. So the non-essential ones, these are ones that we make in our body. So we can make these ones, so we don't need to get these. The essential ones are ones that we can't make, we must get from our diet. So we must get those from protein sources, which is why we must have protein as part of our diet in order to have this complete suite of amino acids to make the proteins that we're made of. And we can get these complete protein sources from meat, fish, eggs, dairy, cheese, but also vegan alternatives, so things like tofu and soy milk as well, and any other legumes as well. So we can get these complete protein sources. But we're focused on meringues because we're focusing on eggs here. So looking at the eggs, now we're going to go, so we talked about the proteins, we know they're made up of amino acids. Now we'll go one step further now and we're going to build onto individual ones, the different properties that they have and how they interact. So this here is egg white. We've got little proteins in our, and the blue is the water. So the egg white's about 20% protein in water. So we've got proteins in our raw egg white. What are we doing when we're making a meringue? Well, we know the first thing that we do is we whisk it up. As we whisk it up, these proteins that are in their native state, so you can see that they're all complexed up, they're all in the nice native state, lots of interactions held together. But as we are whisking up, we now unravel them. That's a process called denaturing. So we've now unraveled them, we've introduced lots of air bubbles, which are these white circles, and then we keep on whisking this mixture, and eventually we get to this lovely foam. So we've got lots of bubbles now, all with this wonderful matrix of these proteins around them. So that's the first bit, that's what we've got making our meringue. Now we'll apply what we just covered on the last slide, talking about amino acids. Let's have a look in a bit more detail. So the same bits across the top. Here is our long egg white protein made up of amino acids. So this is a amino acid or peptide sequence with those amino acid building blocks as we saw before. And I mentioned that we had, each one had a different code, but dependent on the different side chain that it's got. So I've broadly just categorized these side chains as either this red or blue. So they are different, A, B, C, D, but I've broadly labeled them as blue or red. And that's because of the properties that they have. So I've broadly called the red ones hydrophobic side chains, or greasy, or therefore not liking water. And the blue one I've called hydrophilic, or polar, or they love water. So I've got two classes there, and how is those difference in properties going to affect, or do we utilize that on making a meringue? So applying all of that now back to the top diagram again. So in our first one there, we've got our native state proteins. So we know now, we've just talked about two different types of side chains. So set in water, the blue ones that love water, the hydrophilic ones, they're going to like that. So they're all focused, they're pointing outwards. The hydrophobic ones that don't like water are pointing inwards. So think of that is your tertiary structure of that protein as it's all folded up. When we've whisked it to make our meringue, we've opened that up, so we've now revealed all of these ones. The ones that are red are not very happy right now. But then we're incorporating these air bubbles, and what's going to happen now is they're going to begin to sort of like mold around those bubbles, and we're going to end up with this nice little interface here, whereby you've got the ones that like water are going to be pointing towards the water, and the ones that don't like that are pointing more towards those air bubbles. So therefore, we've got this really nice built-up matrix now, nice and stable, and that's stabilized that protein network. So you can see from that last 3 or 4 minutes how we can build up exactly what is going on. Just taking egg white in a bowl and whisking it up, there's an incredible amount of science and chemistry that we can access through that. And that's what I love to do in my talks, is to try and introduce these topics. So one of the students amongst us, you'll be covering protein structure and function and amino acids as you go through your career time at school and into degree courses as well. And it's things like this is a great introduction to it, and hopefully that can then be applied into any other research that you may go into beyond that as well. And one final thing to finish off, I like to do a little experiment. So just to finish off with some more images, here is a little experiment that I did with some meringues. So we've got the ones in the middle is perfectly whipped, just egg white and caster sugar. The one on the left, I've deliberately over whipped, so I've gone a little bit irregular with my beating, and I've done it for a bit too long. And the one on the right is exactly the same as the one in the middle, but I've added a little bit of acid in there. Acid's really great when you're making a meringue, helps to neutralize the charges on the proteins and help them mix together. And so you may see, if you look at your meringue recipes, you may see cream of tartar added, you may see white vinegar added, you may see lemon juice added. All three of them examples of acids. One of them has come out of a bottle, one of them has come from a fruit, and one of them is a white powder out of a tub. All acids, all doing exactly the same thing. And you may just be inadvertently following a recipe, putting it in, but there's a lot of science going on there. There's a reason for adding it. And so what we did, I took those, broke a little bit off each, and then we imaged them under a different microscope now in our engineering building, so we can look at structures. And here are the results. So we can see visibly by eye that they got better as we went along, but let's look at the structure now. Then you can see now that those bubble size that we've got, the structure of our over-whipped one, they're quite small. As we then go to our perfectly whipped one, a bit better, and now this really stable meringue we had with the extra acid in, we can see we've got larger bubbles now, much more stable, really nice looking structure of the meringue. And it was visibly you could visibly see it by eye, but it's nice to show it with a microscope as well. So that brings me to an end. Thank you ever so much for listening, and I hope you've learned a bit more about the science behind baking.
We do have time for a couple of questions, if anyone has any.
It's usually somebody asks me what's Noel Fielding like. That's usually the first question, whatever talk I give.
What happens if you use cane sugar?
Cane sugar? Well, I can't say I've used cane sugar in it, but I think it'd be relatively down to the refinement level of your sugar that you've got for it. It's a little bit darker, it's got a bit more moisture in there as well, but we're going to be adding it into egg white anyway, so I think it should still be fine. But maybe that's my next experiment to go and do. I shall report back.
Does albumin vary from chicken to chicken, in that I tried making them in the States and was told I had to use organic chickens?
I've not seen a massive amount. I think the biggest difference is that make sure you're using room temperature eggs is the best thing, because if you're using them colder, then it's a bit of a shock to the system when you're trying to denature them and unravel them. So actually, when they get a bit warmer, they're a lot easier to do that. So that's always helpful. So I would always recommend using room temperature eggs. But I can't say I've seen a huge amount of difference between different ones. And often the recipes will say, oh, you want to use older eggs rather than fresh ones. Again, I personally have not seen a great deal of difference. I don't, whether I have a fresh egg or one that's been there for a bit longer. But I do think the room temperature makes a massive difference.
Okay, I was looking into the science of the albumin when I tried and failed time after time. And it said the albumin would whisk up really stiff, and they said it wasn't, strong enough.
And the other thing is not to rush the process as well, and you want to get your egg white nice and frothy before you're adding any sugar at all. So get that first bit going, and then a spoonful at a time as you go through. And a really steady speed as well. Don't go too fast with the mixing. A nice steady medium sort of speed for whisking is really helpful as well.
Thanks. How much do different sourdough starters compare in their composition? So lots of people have their own sourdough they might have had for years and swear that there's something special.
There will be a lot of differences. A lot of like your typical baker's yeast that you're going to be having will be the predominant wild yeast you're going to have in there. There'll be a lot of similarities, but there will be slight differences, which is why everybody swears by their one being slightly better or different taste. And aging them also helps as well build up a really nice diverse sort of microbiome in there. But yeah, there will be a lot of difference between them.
Is it mainly the yeast or the bacteria that are different, or both?
Mainly the lactic acid, acetic acid bacteria is the big one, yeah.
What sort of pH would that be?
It's about.
Hypothetically, do you think you'd be able to convert a fully baked cake back to its original ingredients?
Nope.
Not at all?
Nope.
Okay.
Thank you. I think that's all we've got time for today. So thank you again to Josh.
Thank you very much.